echelon and reduced echelon forms, two main concepts that will be useful to solving systems of linear equations moving forward. Welcome to part 2 of the first lesson, linear equation in linear algebra. In this part, we will explore matrix representation, row reduction, echelon forms, and solution strategies such as Gaussian elimination. Let's begin with the matrix representation of a linear system. In the last lesson, we emphasized the point that a system of linear equations can be written in the form ax equals b, where a is the coefficient matrix, x is the vector of unknowns, b is the result vector. In fact, throughout the entire course, we will consider this form ax equals b. The goal will be to understand A and exploit the properties of A to solve the system of equations. We will keep today's lecture as brief as possible while exploiting some key ideas. To begin, let's consider an example. x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, and minus 4x1 plus 5x2 plus 9x3 equals minus 9. Let's write the system in the matrix form ax equals b. The coefficient matrix A is given by, and then we have the vector x and the result vector b. This compact notation simplifies calculations and allows us to use matrix operations to solve equations efficiently. But how would we solve this problem? That brings us to our first idea of the day, row reduction. You see, to solve a system, we transform its augmented matrix using three fundamental row operations. The first is row swapping. This involves interchanging two rows. The second is scaling, that is, to multiply a row by a non-zero constant. And finally, row replacement. Here we replace a row by adding a multiple of another row to it. If all that sounds overwhelming, don't worry, it would be clear shortly. Just note that these three operations help us convert a system into an easier form to solve. But what is our objective while performing the row reduction? Our goal will be to obtain an echelon form of the augmented matrix. So what is the echelon form? Let's consider the following augmented matrix and discuss the echelon form from there. A matrix is said to be an echelon form if 1. All non-zero rows are above any rows of all zeros. In our example, we need to swap row 4 and row 2 so that the all-zero row is positioned below all non-zero rows. 2. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Again, in our example, we need to swap row 2 and row 3, which ensures that the leading entry in row 3 is positioned in the column to the right of the leading entry in row 2. 3. All entries below a leading entry are 0. Pause and ponder about this for a while. Let's return to our example and get it to its echelon form. First, we get the augmented matrix from the matrix form. We can get this from matrix A and the result vector B. Now, consider the augmented matrix. Our objective is to get an upper triangle matrix. Hence, we must perform some row reduction to make the lower triangle all zeros. Let's begin with the first column. Other than the value in the row 1 column 1 position, we want all other values in that column to be 0. For the first row, since the value is non-zero, it becomes the leading entry in that row. So no row interchange is required. Now we only need to make all the other elements below the lead entry of the first column 0. Since the second element is already 0, we are left with the third element, minus 4. Here, we can add row 1 to row 3. The question is, how much of row 1 should be added to row 3 to make minus 4 0? If you follow the last lesson closely, you will see that we need 4 divided by 1 multiplied by row 1 plus row 3. Now that we are done with the first column, we go over the second column. For the second column, 2 becomes the leading entry in the second row, and we should make every value below the leading entry 0. Hence, we should make -3, 0. To achieve this, we perform the row operation. We scale row 2 by 3 divided by 2 and add it to row 3. Great! Now, we have just obtained the echelon form. Please take some time to go over this again, because in the subsequent example, we will assume you already understand how to get the echelon form. The next task will be to find the solution to the system. In the last lesson, we performed back substitution to solve for x1, x2, and x3. In today's class, we will learn about the reduced echelon form. But before we do that, it is important to understand a few things from the echelon form. Let's consider the echelon form we just obtained. For each row, let's identify the leading entry. The leading entry for each row is called the pivot. The column in which they are is called the pivot column. Now you should understand the pivot position and the pivot column. In our example, there are 3 pivots. Hence, there are 3 pivot columns. The pivots help us to understand the first and very important question of linear algebra. Is there a solution to the system of linear equations? A better way to ask the question is the system consistent? A system is consistent if it has at least one solution. It is inconsistent if no solutions exist. So how do the pivot position and the pivot column answer the question? To understand this, let's consider the last row of the echelon form for a moment. The last row tells us that 0x1 plus 0x2 plus 1x3 equals 3, which tells us that x3 equals 3. This tells us there is a solution to the systems of equations. But let's suppose for a moment that in place of 1, we had 0 instead. The last row would have been 0x1 plus 0x2 plus 0x3 equals 3, which would mean 0 equals 3. This will be mathematically impossible, and hence, the system will have no solution. The first takeaway from here is the fact that if the last column of the echelon form is a pivot column, then the system has no solution, otherwise there will be a solution. So, while solving a system of linear equations, you should be able to determine if the system of equations has a solution or not by performing the echelon form. Given that we can answer the first question, is the system consistent? Which is just another way of asking, does the system have a solution? We should then be able to move to the second most important question. The answer to your first question could be yes or no. At this point, if your answer is no, then you can stop working on the problem. However, much later in the class, we will try to get the best approximation to the problem even when there is no exact solution. But if your answer is yes to the first question, you want to ask the second question, how many solutions are there? This is because a system of linear equations could have no solution, or exactly one solution, or infinitely many solutions. If your answer to the first question is yes, then we want to find the solution. But even before solving the problem, you will be able to answer the second question from the echelon form. That is, you should be able to tell if the system has only one solution, or if there are many solutions. To understand how, let's return to our example. Of course, the answer to the first question is yes for our example. That is, the system is consistent because the last or rightmost column is not a pivot column. To answer the question of how many solutions are there, we need to look at the number of pivot columns. If there are pivots in every row and every column of an augmented matrix except for the rightmost column, then there is only one solution. Well, you will see why when we perform several examples. However, if there are columns that are not pivot columns, and the system is consistent, then there would be infinitely many solutions. This will make a lot of sense in subsequent lectures when we talk about the notion of ranks, dimensions, and spaces. But for our example, since there are exactly 3 pivots, and there are pivots in each row and column, then there is exactly one solution. Finally, what is that solution? The answer to this question will lead us to the reduced echelon form. Recall the conditions for echelon form. A matrix is in echelon form if 1. All non-zero rows are above any rows of all zeros. 2. Each leading entry of a row is in a column to the right of the leading entry of the row above it. 3. All entries below a leading entry are 0. For the reduced echelon form, we will add 2 more conditions to the 3 conditions above. A matrix in reduced echelon form satisfies the following additional conditions. 4. The leading entry in each non-zero row is 1. 5. Each leading one is the only non-zero entry in its column. The conditions are simple. First, each pivot should be scaled to 1, which would mean scaling the entire row where there is a pivot. And second, we should perform a row operation on every pivot column such that only the pivot value is the only non-zero element in that column. Note here that we are only interested in the pivot row and pivot column. Let's see what that would look like in our example. In the third column, there is a pivot value, so we have a pivot column and hence, we should scale the row such that the pivot value is 1. For column 2, the pivot value is 2, hence we should divide the entire row by 2 to scale it down to 1. For column 1, the leading entry is already 1. We copy it to the new matrix. Next, we ensure that each leading one is the only non-zero entry in its column. Next, we need to ensure that the second column only has the pivot entry, which means we should add 2 of row 2 to row 1 to make -2, 0. Finally, the pivot value in the first row is already 1, and it is also the only non-zero value in that column. Hence, we have our reduced echelon form. A beautiful system of equations, and you can easily tell the solution from the reduced echelon form. The solutions are x3 equals 3, x2 equals 16, x1 equals 29. Well, this may have looked quite long to get to the solution, but this is because we spent some time trying to drill the ideas home. Understanding the echelon forms can solve so many of the challenges to linear algebra problems. There is so much more we can learn from echelon forms. We will learn more as we go along in the series. Finally, when a system has only one solution, as in our example above, we will conclude that the solution is unique. To keep this video short, we will end the lesson here. It's time to test yourself. Attempt the questions and leave your answers in the comments section. In summary, we explored the matrix representation of linear systems, learned about row reduction, echelon and reduced echelon forms. In the next part, we will consider a few more examples for systems that are consistent with only one solution and an example of a system with many solutions. We will also consider an example of a system that is inconsistent. In addition, we will introduce parametric representations for solutions. See you then. Don't forget to subscribe and hit the notification bell. And see you in the next episode.